So, Bismillah, wassalatu wassalamu ala Rasulullah. So, we're welcome to the class formally, and then we are going to start. As you can see, we have diagnosis of Alzheimer's disease in the eastern province of Saudi Arabia using computational intelligence techniques. This is going to be one of maybe a couple of series. So we are going to delve into this solution and in depth. So the essence, like I mentioned earlier, is so that people can see what you can do. So what has been done, then you can take a cue, learn some things and see how can you apply it in your own area of specialization. See, this is a paper recently published titled Diagnosis of Alzheimer's Disease in the Eastern Province of Saudi Arabia using computational intelligence techniques. And those are the list of authors. And the paper is a Q1 ranked. So, like I said, it's a form of a kind of a proof of concept. We noticed there's a challenge when it comes to this particular disease. And then we said, okay, can we preemptively do something so that this disease could be, if it could be diagnosed earlier, perhaps some actions could be taken that could forestall or at least reduce the suffering or reduce the complication, prevent it from coming sooner. So the Journal of Computational Intelligence and Neuroscience target intelligence system in the area of neuro and medical applications. So the impact factor is 3.6. So in the Web of Science group and also in Scopus, almost the same thing, 3.635. The 2-year impact factor, the 3-year impact factor, these are all kind of evidence that, okay, such journal is something at least to rely on the content. So if a journal can have impact factor of 4.6 for 3 years consecutively, and then ranking Q1, that means, okay, the proof of concept is a little bit reliable. So the idea is that the model has been built. Reviewers have subjected the work to a couple of reviews, blind reviews, and finally the decisions has been taken. So now we want to look at what has been done in this work. What is it all about? You see, the aims and objective of the work was to preemptively diagnose Alzheimer's disease in Saudi Arabia. Of course, now we're talking of the eastern part where we got the data from. This is real life data. Now, so what is preemptive diagnosis? Preemptive diagnosis is taking medical diagnosis to a totally new level where people that are normal, they appear normal, they are going about their normal activity, they are being made to have the opportunity to get themselves screened. Because what we've gone to realize of recent and has been happening for long is people get sick, but they are not aware. The symptoms are yet not coming. By the time the symptom just arrives, maybe just somebody just complained of a little pain. Unfortunately, at that point, it is getting late. They say, oh, it's late stage. There have been several cases like that, different chronic disease, especially what we term chronic diseases. Chronic diseases are characterized by having a lot of burden to the family, to the victim, and a lot of resources will be consumed in the course of trying to get it cured. And often, because of it is often diagnosed late, so most of them are being categorized as having maybe not possible. But if they could be diagnosed very early, it has been proven that they can go a long way in actually solving the problem and even curing the patient totally. So this is the idea, one of the ideas that we have been working on. So this is a preemptive diagnosis of Alzheimer's disease. It employs few machine learning concepts. So employ machine learning techniques to form accurate prediction to see if someone is suffering from this disease or not at the very early stage. That's the big difference. preemptive. It's not just diagnosis. Somebody visit the doctor will have to diagnose. But we are talking of people, both those who have visited the doctor or people who are just moving on the street, doing their normal activity, thinking everything is okay. Can we make it possible for them to check themselves by asking a couple of questions or making few medical tests in their usual maybe visit to the clinic? So the work utilized feature selection, of course, very important to reduce the number of features required to predict Alzheimer's disease reliably. So the data set is the real-life data set, as mentioned earlier. The utilized classifiers include support vector machine, k-nearest neighbor, one of the very simple method, extreme gradient boosting, and then adaptive boosting also was used. So support vector machine strangely outperform every other system. So at the beginning, before we go to data set description, like I said, we're going to go into the full paper later on, where we're going to look at every step that has been taken. It's very, very important to make a very strong case, for whatever you want to do. Very important. See, we notice several cases of people suddenly suffer from this particular kind of ailment. But unfortunately, and the diagnosis, people usually, because it's usually associated with old age. So often than not, when people start having this, they think, oh, it is an old age, it is an old age. So the disease is not actually diagnosed correctly in an early stage, so that the intervention procedure that could have been put in place becomes very impossible. So this is why, if the early diagnosis, which we call preemptive, that is before the symptoms start coming, we want people to be able to know if they're having such disease. So data sets have been obtained, which actually initially consists of the data was gotten from King Fahd Specialist Hospital in Dammam, Saudi Arabia. So the data set contains a lot of features and several thousands of instances where it has to be filtered to extract the laboratory trace. Yeah, we said it tried. There are several features, maybe not less than 435 attributes, 435 attributes. That is a lot. So we have to extract the data sent in raw. So as an advantage, taking advantage of trying to extract the data took a lot of time because it's a very big data. Of course, a lot of the data sets were repeated data and the likes. So we had to do parallelism. We use parallel computing to reduce the computational complexity of the data filtering. That is, extracting the data was taking a lot of time. Of course, this is not compulsory. This is just a kind of opportunity also to showcase and take advantage of the available technology. So because we noted that it was taking so much time to get the data extracted. So the parallel code, a very simple parallel code was written to make it faster, and it really assisted the work. Then after applying the filter code, and then removing the two duplicate records, because there are a lot of duplicate records. Somebody visit, some people have several visits. So the data set contains standard clinical tests of 152 patients. See? So from thousands of records, it comes down to only 152. So it was a very big filtering that was done. So where 63 of these 152 were positively diagnosed. That is, they were diagnosed people to suffer from Alzheimer's disease, which we call AD. And there were 89 that were negatively diagnosed. That is, they were not suffering from that disease, because this is a classification problem for sure. So it means we have two classes. to deal with. We have the class 1, which is, you can say yes or no. Yes means it's positive or positive. The person is suffering from that disease, and no, the person is not suffering from that disease, based on some test that has been done. So, therefore, while we settle, we were able to extract 152 unique records, then 18 attributes out of the 435 that we initially started with were utilized after removing the columns that contain more than 30% missing values. You see, sometimes you have columns, there are columns there, they are valid features, but we decided that any column that is, or any feature, you know, we have column-wise like this in Excel, this is the feature. Any feature that has missing value up to 30%. You see, usually there's a kind of threshold. We compute the threshold. You divide the total number of how many missing value do you have, divided by the total number of value in that particular column. So if you have any column that has above 30% of the value is missing, then we delete that particular column. Of course, we can treat missing value, but at the same time also, when the number of treatment is too much, it means we're gonna be working with more of fake data. So we don't want this as a case. So we try to trim down those columns that are having issue or that are having a lot of missing values. So this was how we arrived at 18 features, and then 152 samples. So when you have 18 features, 152 samples, for sure there's going to be issue with cost of dimensionality, which we mentioned before. See, having 18 means ordinarily maybe we are supposed to have 18 raised to the power 10 samples to get reasonable result. Now we're having only 152. So for sure we'll have to do what we call feature selection. But let's see how it proceeds. Like I said, it's always good to let the data speak. You have to use this original data, 18 features, then 152 samples. So that is when you have, it's like having 1, 2, 3, 4, 5 features, and then these are the samples, 1, 2, 3, the rows, now and the column. So you take this data, you put it in your own platform, either you use Weka or Python, whatever you use. That's okay. Now, if you look at some of the data sets, these are basic clinical data. At this stage of the project, we're using basic clinical data because of the advantage that it could be obtained in any hospital. Very easy to get. So we don't want to use imaging, the image data, because some clinics don't have image facility. And if we get the images done and so on, but we have some, we want something that is very common. So imagine we have sex, it's one of the attributes, age, temperature, white blood cell, red blood cell count, pulse, platelet. These are basic things that any medical center can produce this result so that people can check their status regarding this disease. So this is under description of data set. So the hemoglobin, the pulse, the respiratory rate, BP, systolic, BP, dystolic, these are the 18, if you count it, these are the 18 features that were finally identified and they will use for the work. Now, the next we talk about is the experimental setup. The experimental setup. See, when I mentioned to us, it's very important, whatever you do, one of the very important things you have to do is, how did you carry out your work? Can someone else easily repeat what you have done? Is it possible? This is very important. See, so this is where experimental setup, you have to describe what you have done, make it possible for someone to be able to repeat what you have done. So when we go back to the main paper later, we talk more details about the experimental. So this is the raw data coming in. If you can draw a very nice flow chart or flow diagram, as the case may be, That would be very nice. It makes your work easier for people to follow. So this is the raw data. We try to do, we call it data collection. I told you we use parallelized data filtering to make the data to be easy to filter the data. Otherwise, my students were running it for like days. But after the filter, after a few hours, they were able to get the result out. So that's the advantage of the parallelized system. It means then we have the data set cleaning. So cleaning it, treating the missing value. If any column has more than 30% missing value, we delete that particular column, and also for others. So then after that, we also have data preprocessing unit. So this is outlier remover. If there's any outlier, we try to check, is there anything, is any data that looks really out of range? We treat it as usual. There's a video for us there earlier. We discussed how to do preprocessing. Then we have the missing value imputation, and then also normalization. If the unit of the values are totally different, we have one feature with maybe 1,000 with a maximum maybe 1,000 or 1 million. That is, if there are feature X1, X2, X3, the units are different, of course, but this one is having very high value. You can have maybe 200,000 here, 40,000, but here is 0.2, 0.1. You can see the values here is totally small. Why this is bigger? Usually when you normalize so that everything will be in a range, you can normalize this one to become between 0 and 1, as the case may be. So it has a lot of advantages. However, the target shouldn't be normalized for classification. Even for regression, we should avoid normalizing the target. And if you normalize target, you must remember to denormalize after the result has been produced, so that you'll be dealing with the actual value at the end of the day. That is for the target. Now, then the next, we also have SMOT here. So SMOT is used to SMOT is used to treat. SMOT is used to treat. You can see here, this is a sign here. This is called imbalance. There's data imbalance. You can see here. This, we have class B and class A. They are not balanced. We use SMOT to balance the data. Sometimes, when I told you here, we have 63 and 89. See, we're having 63, yes, people who are suffering from the disease. And also, the other one is 89. We have 89. This is imbalanced data. That is, we try to let the number of each class to be almost equal. But this is fairly okay. So in the SMOT, we're going to discuss in detail later also. So we try to balance the data. Then after that, so modeling now starts. This is model training, use each of them. You see, you know, when you do modeling, I told you about hyperparameter tuning, very, very important. We do the hyperparameter tuning, where you have a kind of, it's going to be going back and forth until optimal values are obtained. So this is very important. Also, when you get to the feature selection, you want to check different features, which feature are going to work for me, which one is the better one, especially when you have 18 features with just 152 samples. Definitely you need to do feature selection to be able to hopefully get something better. But we see later how feature selection really assisted or otherwise. So the feature selection also, there's going to be a kind of back and forth. You see, you keep trying it. So this is model testing using accuracy, recall, and precision. Of course, the confusion matrix also is very important that have been used, confusion matrix. So you keep trying different feature selection until the optimal set is actually obtained. That is, what is the optimal features that will work for us? Usually we want the minimum possible, because so the lesser the number of medical tests people need to do to use the machine learning model predictive solution, the better. So you don't want a model that someone needs to do like 18 medical tests. That is going to be a lot of money. Even if they are very simple, even the time taken to collect the blood and so many stuffs. Like I mentioned earlier, what we are working on is we hope we are going to get to a point that we are going to have questionnaires that people does not need to visit the clinic before they diagnose themselves of some of these chronic diseases. This is going to be the next stage we try to explore. That can we even avoid going to the clinic, asking them basic questions? And from this basic question, we can be able to know that someone is already suffering from a disease or not. So that the idea of preemptive diagnosis is to take diagnosis to pre-symptomatic stage before people complain. They are living fine. They are going to their offices. Everything is normal. However, human system is so strong that, you see, chronic disease do originate at early stage. People don't have any symptoms. They are not even aware. By the time they start complaining, usually it is already at the late stage. So this is what we try to capture in this kind of system. So when people are still going about their normal activity, thinking that they are okay, we want to quickly detect that, oh, something must be wrong, so that they can look and go and for further checkup. So this is the idea. So to do such a thing, we're still struggling now to try to reduce the number of features. But later we hope we can be able to move to the stage whereby we can actually talk of using basic questionnaires, normal questions from people, of course, that will relate to their health and status, maybe kind of the kind of lifestyle they are using, how many times do they sit down in a day, how many times do they exercise, what are the activities they carry out, which kind of, basic questions have been actually seen to get some reasonable results of recent. I think I showed us in one of our previous videos where we took a data set that used questionnaire to diagnose diabetes. So I want to believe these are extendable to other chronic diseases. Now, so having tested the model, so this is the experimental setup. So in the hyperparameter tuning, to shed a little bit more light, you see, for each of them, so hyperparameter tuning consisted of we have the C, the regularization factor, which we call the cos, the gamma, and the kernel. And then we have the range. These are the range upon which they were searched. You know, you search in a range and then pick the one that gives you the best result. That is hyperparameter tuning. We've explained this also in our previous videos. Now, then the hyperparameter grid of KNN, which is going to be, you are going to look into nearest neighbor. And also, this first thing is to look at the nearest neighbor. How many N neighbors do we need to use? So it is search between 5 and 39. Also, we need to check the distance measure metrics, like Minkowski, Euclidean distance, Manhattan. Those are the ones check. Then we have the hyperparameter also for other boosts. The ranges were listed. We also have for the XG boost, ranges also listed accordingly. Then this is the summary of the hyperparameter tuning, the ones that actually perform better. These are the best values, the one that's achieved the best result. So for SVM, you can see here, we have SVM, we have KNN and others. So now, two categories. Like I said, we're going to talk about those diseases later on, where we do without oversampling, with oversampling. See, when you try with oversampling, we try to bring the lesser class to be at par with the, we have 89 and I think 53. If I'm not mistaken there. Yes, sorry, 63. Yeah, 63. 63. So we want to bring this to be at the same level with this. We call it oversampling. So then we are without oversampling, which means you use the original data as the case may be. So these are the kernel that work for them. These are very important information that you need to make available when you build the model. People should be able to repeat what you have done. Otherwise, that's going to be a big question on what you have reported. So if anybody wants to repeat this experiment now, you just need to open your Weka or open your Python, put in the cos, which is the regularization factor C, the gamma value, the kernel, and then you run it, you get the same result that this is getting. That's why hyperparameter, the optimal value has to be specified. This is compulsory. Then we have the feature selection, which is the sequential forward feature selection algorithm was utilized. See, there's a very special a feature selection method called sequential forward feature selection algorithm. It was used. So which automatically chooses the feature set that best suit each algorithm. See, it's a totally new idea about feature selection. We didn't use the same feature for all the algorithm, but rather we allowed each algorithms to check all the features and see which one is good for you. So in that sense, we see here that SVM identified 13 as the best for itself. KNN got 6, AdaBoost 10, SDBoost. I'm always a fan of people who can get lesser feature. We want to reduce the feature. Imagine KNN was able to achieve almost close accuracy to SVM using only 6 features. Only 6: age, respiratory rate, hematocrit, MCH, RDW. Just 6, and it's getting 95. So we are going to look into the detail later in the main paper and then see how did you come back to really finally say that, okay, support vector machine is the best. Of course, support vector machine is here with 95.56, a little bit better, very minimal difference. So, but it's having 13 features. Why this is having 6? This is less than half of it. To me, this is really a very promising thing to investigate further. Now, but each of them has been made to allow to select features that work for them. This is called the sequential forward feature selection. Like I mentioned the other time, there are several types of feature selection you can actually use, depending on the problem and the one that worked for you. So we have the principle of let the data speak. Let the data speak. Yeah. So this is the idea that has been totally explored here. We allow each of the algorithms to select what works for them without imposition. Of course, it has its own challenges, as we are going to discuss also later. The result summary actually indicated that SVM achieved the best performance among the other classifier, considering the accuracy of this is what it has achieved, a recall of this, and it's using 13 features. Like I said, this needs a lot of analysis. Need further analysis, yeah. Of course, we are getting the best result there. And most importantly, this is what we call confusion matrix. This is confusion matrix. You see, we want to see where is the mistake coming. You see, this is false positive. So this is true positive. This is true negative. These are the correct predictions. It means there are 87 Alzheimer's disease, and they are predicted as such. 83 non-Alzheimer's disease, and is predicted. These are the correct prediction. You see, we call them true positive and true negative. You see, but here, this is supposed to be Alzheimer's, but has been predicted to be non-Alzheimer's. See, this is called false negative. See, false negative. And this is the big issue. Why this is false positive? False positive, 6. It means there are these 6 people are supposed to be, these 6 people, they are supposed to be non-Alzheimer's, but they have been predicted to be non-Alzheimer's. They are predicted to be suffering from disease. Meanwhile, they are not supposed to be. They are part of this team, but it was mistakenly predicted here. So we call this false positive. Now, in medical system, so false positive, these are mistakes. This is error. This is another error. But this type of error is a serious error in medicine. You see, and I will explain later. We'll see later in a further discussion, hopefully maybe next week. We're going to see why we settle for SVM actually. You see, because the mistake coming from SVM, the majority of the mistakes are coming from false positive. False positive is saying someone is not sick, you see, but you are predicting the person to be sick. So the person will go and check himself or herself and find out that he's not sick, and he'll be happy and go back home. So it's a mistake that has lesser evil. This is lesser evil, yeah. It's better to predict that someone is sick, but is not sick, because you finally make a follow-up with the doctors and they find out that, oh, we are sorry, our machine learning system made a mistake, you are okay. So you can go home, enjoy. This is still better than this one is you are predicting that someone is not sick. Meanwhile, he's sick. This is false negative. You say, oh, you can go home and enjoy yourself. You are not sick. Everything is fine. Meanwhile, the person is sick. He could develop complication that worsen the situation. So that is why if you see a particular model that is achieving lesser false negative, the mistakes that are more are coming from the false positive. We a little bit prefer it to another model with maybe closer accuracy, but having more false negatives. Maybe the other one is having like maybe 5 false negatives, and here is having only 2. So this is one of the discussion that we do consider when we select which one is actually better. But like I said, we're going to discuss this in further analysis and exposition of the work. And of course, also the ROC curve, so which is showing that the prediction is really good. So we want it to be closer like this. This is what we are expecting. So to be 100%, but now it's not bad. This is better actually. See, it's getting 0.97 in this case, so which is a good result. So this is a summary of this work. So we are going to give opportunity for people to ask questions, because this is just the initial stage, just summarize what we have done and the result obtained. Then we are going to go the next week, inshallah, we're going to go into the real paper, the actual paper, page by page, then try to see what has been done, how it has been done, what led to this particular summary that has been made. So thank you for this. So, and we're going to give room for question, either related to what has been presented or any other question as we might have. Thank you very much. And this is what we are going to have for the day.